welcome. We are the IAM3D Solar Water Harvester team. I am Trevor Solorzano, and this is Tomika Walkin, and this is Daniela Montero. We will be talking to you about our project. Okay, so a really quick outline of what we're going to be doing today. We're going to be talking to you about the competition we're involved in. As mentioned, we were part of the IAM3D competition. We're going to be talking to you about the literature survey, the survey-related standards, our 3 alternate designs, our proposed designs, the simulations we've done on that design, and the design experience that encompasses the whole project. We'll be talking about the Gantt charts and the division of responsibilities among our team members, and a conclusion and our future work ahead of us. So what is the IAM3D competition? It is to re-engineer existing products or create new designs that minimize energy consumption and or improve energy efficiency. And what IAM3D stands for is that you see here at the bottom part of the screen, is innovative additive manufacturing 3-dimensional. So our project, our solar-powered water harvester is a 3D printed solar-powered water harvester that is lightweight, it's portable. What the idea is to provide potable water in places where there is no water. It produces water out of thin air, out of the humidity in the atmosphere. And so our goal for this device is to produce 1 liter of water per hour, and it can do this in either 90% or higher humidity levels. It is better for the humidity levels to be 90% or higher, but we already have done some research on that. 50% and higher is ideal for our device. Just this will be able to do the 1 liter per hour. So our literature survey. I'm going to be handing this over to Tomika Walkin.
Since our device acts so similarly to a dehumidifier, it's only right that we should rate our performance evaluation based on that of a dehumidifier. And how those are rated are based on a moisture removal rate, which is basically just the rate of condensation that occurs during the dehumidification process. Another factor that is taken into consideration in a dehumidifier is the energy factor, which is measured in liters per kilowatt hour. For example, with our device, we want to produce 1 liter per hour. With a factor of 1.5, this would require an energy of 0.681 kilowatts. So we took into consideration different forms of energy. The first one being piezoelectric, which is just energy based on a difference of pressure. The second being thermoelectric, which is energy based on a difference of temperature. And of course, solar energy, which is energy produced from the sun's light. We determined that solar energy would be the way for us to go, with cell efficiencies ranging from 7% to 40%. And for our purposes of producing the 1 liter per hour with energy rating of 0.681 kilowatts, we need a cell a size of approximately 144 inch squared. So this is one of the projects we found when we were doing research on this project to Caro. How it works is the fan draws in air from the top of the device through the little slits in the top. Air is directed to one side of the device over the heat fins. The white plate that you can see in the middle is the thermoelectric cooler, which allows the right side of the fins to be cooled. Once the humid air comes in contact with this, it will condense on those fins and fall into the bottom of the collection chamber. And I'll hand it off to Daniela Montero, who's going to continue the literature survey.
Okay, so for this study, we needed to know how was the humidity here in Miami. Right now, we're gonna have in consideration just Miami, Florida. So in Miami, there is a humidity level between 96% and 46%. So it oscillates throughout the year. And here the blue line represents the morning humidity level, while the orange one represents the afternoon humidity levels. So the optimal time to start using the dehumidifier, it will be during the morning. The other component that we had in consideration was the heat sink, which breaks down the boundary layers of air and wraps it around the surface. So the cooling capability is determined by the surface area, metallurgic, and the impact of the heat sink structure on the airstream. Here we have an image that represents the thermoelectric coolant, where the heat is absorbed by the cool side and then it's rejected by the hot side. These are the related standards that we had in consideration. We had FSEC, which is mainly for the use of solar cells. We have ASTM that we use it for the material we're going to use, because we're using 3D printing manufacturing technique. The material we're going to use is going to be PC, polycarbonate filament. So the test we're gonna be in that material specific. We're gonna have also in consideration NSF, ANSI, where we study the properties of drinking water, that it should have the exact minerals for this type, and the SME standards for the corresponding competition. This is the first design that we had in consideration, where the air should come in through the upper side. It should go through the fan. Then we will have a radial fin, and then the air will go out at the end before the funnel. Then the second design we had in consideration, it was a horizontal water collector, where we will have 4 fans and more air will come in. So more air will be able to be compressed in the compression chamber, and then this will be the water reservoir. Finally, we have the third design, which is the vertical water collector, where the air will as well come in from the top side on the left, then go through the fan, the same through the left side. It will go through the hot side of the filter plate, and then go up through the cold side. So when hot air touches the cold fins, the air will condensate, and that's how the water will start dripping, and then the dry air will go out from the design. Here we have a comparison of our 3 designs. So for the first one, yes, we have larger surface area for the air to come in. However, it wasn't that sufficient, because with the radial fins, the cool air will mix with the hot air, and it wouldn't be as efficient to condense the air to water. For the second design, yes, it will be more efficient, more air coming in, more production of water, better dehumidification rate. However, it will be more expensive, and it will be heavier as well, because we will have more components to add. So it will conflict with our goal that it's a portable design. Finally, we came with the final design, which is the vertical water collector B, where it will be more efficient, where cold air does not mix with cool air. However, it's a more complex design. I will leave this part to Trevor.
Okay, so basically our proposed design, which was the final design, it was the vertical design B. Here we did a few simulations on airflow using Flow Express and SolidWorks. We were able to identify where exactly the air was running through, and so here you can definitely see the air comes in vertically through the top of it. There is a fan here, and then you do have the air funneling through this area. This is where all of the different the fins are for the heat sink, and then it will come down through here, and it will also be going through the condenser fins that are located right here. And then that is where all the water would come down and it would condense, and then it would come all the way down to the bottom. There's an exploded view of what it all would look like if they were to take it apart. And then here you have just a really good idea of what it's going to look like. So our global design components, basically we just wanted to tackle a few ideas of air quality. We have to make sure that the air quality in surrounding areas, such as Miami or wherever we go with this, will be clean enough, because since the water is coming from the atmosphere, we want to make sure that it's safe to drink. We have to make sure that pollution levels aren't so great that maybe even a filter could even handle that job. We also have to identify that the consumption rates of different athletes are different in different sports. We mentioned our target audience as being like a cyclist or a hiker. So we have to identify the different kind of consumption rates for these different athletes. We have to consider that also there's limited water in certain areas. So this is a problem we want to fix. We definitely want to tackle that. We will be able to provide water where there is no water. And so our design experience, through the different standards we used, the ACM, the FSCC, the different standards we use help us to, I guess, move this project forward and to keep within the guidelines, as well as the IAM3D competition standards as well. We have also have to take into consideration environmental issues, but we actually are helping the environment. There's no byproducts in any way of using this device. As we mentioned, it's solar powered and it creates water out of the air. The cost aspect is it's relatively inexpensive because when we analyze, when we take into consideration all the different components of this product, we understand that most of these products are readily available. These thermoelectric plates are mostly readily available. 3D printing is becoming more and more the norm. The different 3D, the only issue we can come across with feasibility is the 3D fins. We want to see if we can get them either 3D printed or perhaps use them in a certain configuration. So that's more of a custom job, so we have to go more into detail with that as far as research goes. And our lifelong learning, just through research and the team experience, teamwork experience, it helps us to just, come across good lifelong learning. And our project timeline, we are on track with what we were planning to do. Right now, we're in the model optimization and simulation area of time. Now, we've already been ordering parts, so I think that our prototyping and building and constructing of these different things can come in a little bit sooner than we expected, which is really great news. And we will, as soon as we build the prototypes, we'll begin testing them immediately. And our division responsibilities, as you can see here. So our future work, what could we do to make this better? We can include more powerful fans, but that means we have to be able to supply that with a sufficient amount of power. So we have to do more research on solar panels and what possibly can we do to either increase the power coming from those or the quality of the solar panel. We have to be able to consider that because this provides water and where there's no water, maybe this can help disaster relief situations or provide water in power restricted locations. We can also consider larger travel packs for these things, just optimize it so that it produces more for, let's say, more than just one person. Now, so basically for the competition, what we have to do right now is we have to submit in 5 days our proposed plan, our proposed idea, the project that our design. And after that, we will also, the finalists will be chosen in June. So once that's thrown in there, we will see if we become finalists, and our project will continue after that, as I mentioned, with simulations and different and more research on just the whole entire device. And there's our poster. Thank you so much for listening. Any questions?
Thank you very much. Any comments? Yes.
I was looking at your design matrix, and one of your alternatives you said was too expensive, and the second one you said was more complex design. Those can't be compared to each other. So, I would have hoped you would have said, the cost column would have cost-related information. Complexity would have been a separate area. That's one. Second one, cleanliness. How do you handle, or are you planning to handle how clean the water is?
Okay, so
This process.
Okay, because we're using the condensation process. When you condensate air and it becomes water, it's pure water. But because it doesn't have any bad bacteria or virus or anything, it as well does not have minerals. So one of the things to mineralize the water that we're having consideration is to use Himalayan salt, which has, in relation to the minerals that regular water has, it will mineralize the water. However, studies have shown that 100% water, 100% pure water does not have a bad effect in human health if they have a good eating habits. However, just to eliminate that part, we mineralize the water, and that's how we make it drinking water.
Okay, so really where my question plays, when I leave my car out in the parking lot and it rains at night, and I come back out and there's water stains all over the car with little black spots everywhere, what in your system will prevent the dust that gets into humidity from
Getting
into my water supply?
That's true. After the fan, we're putting a filter of a porosity of 0.1 milliliters or millimeters to prevent the dust to come into the system.
What is the envelope of the system itself? Because you were saying also about the size constraints and how heavy it's going to be. What is the envelope? What is the total size as of now? What do you consider?
Excuse me. So because our goal was 1 liter, the actual bottle will be roughly a liter or more. As far as the diameter goes, we were taking a lot of dimensions in metric units. So we were considering making this about 8 centimeters wide at this location right there. So that's going to be about 8 centimeters wide. We really tried to focus on making a really friendly user-friendly interface. That way you can hold it. It's not too big, so it's not obtrusive. It's something that an athlete can take with them wherever they go. So that's kind of the idea that we have going there. And the height of that would, I believe that was about 80 centimeters. Yes.
So you're literally looking at the size of a water bottle, basically. It's your envelope right now, right?
A water bottle
What I'm going for is the actual size and maneuverability of this. Having it, this is the size of the component.
Right.
Have you guys already made sure that with this size, I can produce that amount of water based on the power that I need to create that amount of water based on size? That at least I'm close to it, right? I understand that it's a preliminary concept, so it's okay. But if you're pretty much in line with the size of the envelope of the mechanism to provide that amount of water that you want. 1 liter of water is pretty big for something about this big in generation versus time, depending on how long you're doing. So something I just brought it as a comment itself.
Okay.
Okay, so I have a couple of questions for you guys. Before you mentioned that you have a 0.1 milliliter filter. Why is that?
To prevent the dust to come into the system.
But why 0.1 milliliters?
Because it's the one that we found that has less dust coming to the system. Yes, there is commercially, the one that is used commonly is 0.4, but the ones that we put in our homes are usually 0.1. So that's why we picked that one.
Okay, typically whenever something is for your home or something like that, there's an ISO standard behind that. All filters have an ISO standard. So make sure you know what ISO standard backs up your claim for 0.1 milliliters of a filter use, okay? And then the other thing, what is the solar cell efficiency goal? You guys want to make it efficient, but what is your goal?
So I guess I can answer that one. Our efficiency, or our goal entirely, is to be able to provide this to somebody with a cost-effective idea in mind. So our solar panels, we've been researching different kinds of solar panels. We're not necessarily creating them. So we're trying to see what's out there in the market. This one, we mentioned 1 foot, an area of 1 foot cubed, 1 foot squared, sorry. This device was providing just the sufficient amount of power necessary to provide power for the Peltier pump and the thermoelectric cell and also the fan itself. So it completely took care of both of those aspects. So as far as efficiency goes, that will fall in line whenever we decide on which solar panel is the right one to use. But right now we're looking for cost, and then we're looking for the power that it can provide. So efficiency will just kind of be something that, oh yeah, this has efficiency of this, if that makes any sense.
At the end of the day though, you should be able to calculate, have a number for efficiency.
For sure.
And also, how will you be able to clean this? I mean, if this is for drinking water, I mean, you have little crevices in here like that. When I drink something, I don't completely clean it out, and then when I have to use it again, I don't want it to have gunk or mold growing inside of it. How are you guys going to mitigate that?
So, well, part of the design, we want to be able to have it, so you can take it apart easily. So we're trying to make these components really easy to remove. We're gonna have different slots for it. So why remove it? Because over time, yes, gunk will accumulate different, maybe perhaps mildew because it's water and air, all the different things, especially when it's condensing. And So we want to be able to make this device cleanable, but also to keep this device from getting dirty inside. We're definitely going to consider that really, really good filter that we were mentioning before, so that the dust doesn't enter, which that's primarily where all the gunk is going to come from, the bacteria and the dust in the air. So we're trying to stop that from even entering before, all the problems occur.
Filters do, I guess, choke at one point or another. So in other words, your design is going to lack efficiency at one point. How do you know when would that point be? How easy is it to replace that filter? Have you guys considered those aspects?
Yeah, we've, that should be in the prototype. When we build our prototype, we're going to definitely experience how to do testing with that. So that will be information that we'll be gathering later on in the research.
And also, the font for your guys' the titles on your PowerPoint slide, so if you go back one slide, it's a little bit hard to read because it's white on white, even though it has the outline. Just make it another different color and it'll be easy for your audience. Thank you.
Any other comments, questions, Dr. Copeland?
Just something very quick. Is it the competition's in September? Is that it?
In August.
In August, and the finalists is chosen in June. And what happens if you're not chosen as a finalist?
Yeah, we still have to finish the project.
And you will, and
Of
I'll be presenting in December,
Mhm.
regardless.
Regardless.
Okay.
Greg, you're fine. Well, thank you.